Quite often in a math class, what you'll see is that after you learn a new trick, a new skill, that you learn its applications. And the same thing is true here. We learned how to solve systems of equations in 3 different ways. We learned how to solve them by graphing, by substitution, and by addition. So now comes the application of that. So we start applying that, figuring out where we use that, where you're going to come up with a system of equations. And that starts with problem number 4 in section 4.4. Now what this means for you is that we're going to end up having to not only solve a system of equations, but we're going to have to set them up as well. So a lot of times people regard the application problems, they don't call them application problems, that's too much of a polite word. You call them word problems. Word problems like, ugh. It's just like some people use climate change, some people call it global warming. All right, so we're going to solve application problems here. We're going to focus a lot of our work on setting up the system of equations, not so much on solving it. We'll practice a few, we'll finish them all out. But the thing is, if there's 2 unknowns, you're going to have to write 2 equations. It starts here. 2 angles are complementary. That means that the angles add up to 90 degrees. So that's actually kind of telling you one of the equations. They're giving you a nice little drawing here. You can see that this is a right angle. So the 2 angles add up to 90 degrees. The measure of the larger angle is 4 times the measure of the smaller angle. Write 2 equations that model the situation. So can you come up with the first equation? What's the first one there? X plus y equals 90. Thank you. So the 2 angles are complementary. So x plus y equals 90. Good. Now the larger angle is 4 times the smaller angle. So I need another equation. The larger angle, certainly the way it's drawn here, is x. So what equation puts together x and y in that way? Not quite. We don't have to worry about the 90 part here, right? Right now it says the measure of the larger angle is. So x is 4 times the measure of the smaller angle. So that is suggesting an equation. Yeah, x equals 4 times y. So the larger angle is 4 times the measure of the smaller angle. 4 times y. Now maybe for this first one we'll actually solve it, but for a lot of these we're not going to take the time. This one's tailor-made for substitution. I'd take this, plug it into the first equation, and end up with 4y plus y equals 90. So 5y equals 90. If 5y equals 90, what does y equal? 18. That's a little degree symbol here, in case you're curious. If y is 18 degrees, what does x equal? Four times 18 would be 72. The units there, again, would be degrees, because we're talking about angles. And that's it. There's your 2 solutions. Make sure as you do these types of problems that you give me both an x and a y. You might see it written in the book like this. 17 and 22 is an ordered pair, but same thing. All right. Let's try another one here. Problem number 28. Are we okay with problem number 4? All right. So problem 28. I was thinking about that just this morning. Thanksgiving is not too far away. Woohoo! Trying to decide if I want to cook it or farm it out. Maybe go someplace. So there are a total of 510 calories in 6 ounces of turkey and 1 slice of pumpkin pie. There are a total of 580 calories in 4 ounces of turkey and 2 slices of pumpkin pie. All right, so one of the challenges you're going to face in these types of problems is that they don't tell you what variable to use. They don't tell you what the variable represents. My suggestion to you is that you try and choose something that reflects and represents things in the problem. Like, let's see, we've got 6 ounces of turkey and 1 slice of pumpkin pie. That's 510 calories. So let's choose some variables that represent the number of calories in each of these things. How about T and P? Does it work out all right? So T would be the number of calories in 1 ounce of turkey. And P is the number of calories in 1 ounce or 1 slice of pumpkin pie. So this is problem 28. T is the number of calories in 1 ounce of turkey. P is the number of calories in 1 slice of pumpkin pie. So those are our 2 unknowns. In order to solve, we're going to need 2 equations to solve those 2 unknowns. So, okay. Let's see. Let's get back here. There are a total of 510 calories in 6 ounces of turkey and 1 slice of pumpkin pie. Can anyone give me an equation for that first sentence? Yeah. All right, 6T plus P equals 510. Good. 6T plus P equals 510. All right, I need another one. Let's take a look back and see what we can get for the other one. Jimmy.
4T plus 2P equals 580.
Good. 4 ounces of turkey, 2 slices of pie equals 580. Perfect. So, 2 unknowns, 2 equations. 4T plus 2P equals 580. Now, the big chore in this section is to try and set up your system of equations. So let me stop here. Are you comfortable with where we got these 2 equations? Is that yes? Thumbs up? Okay. All right. Now let me just kind of tell you the solution then. P equals 55 and T equals 180. And that must be one really thin slice of pumpkin pie. Pumpkin pie is loaded with calories. Not that I don't love it. Pumpkin pie is awesome, but calories. That'd be a bummer if 180s on track for an ounce of turkey. Not sure on that one. That's looking pretty lean for the pumpkin pie, though. Okay. Let's try problem number 32, unless there's some further questions or thoughts on problem 28. Autumn? Oh, I had to solve these. I'm not showing that part. What I want to practice right now is the setup. Okay. So as far as solving this is concerned, an easy way that you could solve this would be by the substitution method. You can move the 6t to the other side. And from this equation, you get P equals 510 minus 6t. Take that expression and plug it in here. That'd be one way. Another easy way would be to multiply the top equation by -2. and then add the two equations together, you'll get the P to cancel it out. So you can do that by addition. But right now, what I want to focus in on is just setting up the equations. Because in my experience, most people can solve the equations once they get them. And I want to give you a lot of practice with the setup. Problem 32. So the Boy Scout troop earned $24 by recycling a total of 330 beverage containers. The recycling rates are shown below. How many of the small capacity containers, how many of the large capacity containers did they recycle? Hint, 5 cents is 0.05, 10 cents is 0.10 in terms of dollars. Again, you need some variables here. Does the problem kind of suggest itself of some variables? What variables can I use to represent these two different types of containers? I like that. S and L. Small and large. Sure, why not? Now, what about this problem does S represent? It's not just small containers, but what about the small containers? It's how many of the small containers, right? So let's write that down. Let's write both of these down just to keep track of it for ourselves. S is the number. I keep on putting hashtag. It's just my thing. It's a number. I'm just writing, being lazy. Number of small containers recycled. L is the number of large containers recycled. All right. So that's our two variables here. Hopefully we have a good understanding of those. Let's see if we can't come up with a couple equations here. And at least come up with the first one. They recycled a total of 330 beverage containers. So Rochelle, what's the equation there? No, I'm talking about this one. Madison, maybe some help? Yeah, there's a total of 330 beverage containers recycled. So the number of small plus the number of large containers equals 330. So S plus L equals 330. All right, so that's one equation. If you notice, we have two unknowns, so we need another equation. Where do you think that other equation is going to come from? Any suggestions? Where's that other equation going to come from? All right, something about the price. Is there some numbers in this problem we haven't used yet? $24. We haven't used the $24, right? All right, so how do they get that $24? Not quite. Not quite. So the $24, it's not just S plus L, right? Because that's the number of containers recycled. Good. So we get 5 cents per small container recycled. So 0.05 S plus 0.10 L. So 5 cents for every small container plus 10 cents for every large container. And you get a total of $24 out of all this. Yay. I'm focusing here on coming up with a system of equations. So this is the big part of this, is getting these two equations. Now I think you're okay with the first one, but do you see what's happening with the second one? Think about it. If you had, say, 6 cans here, 0.05 times 6, that'd be 30 cents. If you have 10 cans or 100 cans, however many cans you have, you're getting 5 cents per can, so you have to multiply. Then over here, you're getting 10 cents per container. So again, you're multiplying, and you got a total. Boy, when you see that word total, boy, that little light should go off in your head. Total means you're adding up a couple things. And we're going to see that a couple times here today. There's your system of equations. If it was up to me to solve this, I wouldn't solve it like here. I don't think many of you would be happy with dealing with decimals here, right? So what could I do? Perfect. Let's multiply everything by 100. And if you multiply everything by 100, that's going to move the decimal 2 places to the right. So we'll get 5s plus 10l equals 2400. And then up here, s plus l equals 330. Like that. On your exam, I'm going to ask that I'm going to give you 2 problems side by side. I'm going to ask you to solve one by substitution and one by addition. Other than that, on the exam, you're going to be free to solve these any way you want. If you're going to solve by substitution here, I'd move the L to the right-hand side and get S equals 330 minus L, and then substitute that expression into the other equation. So it'd be 5 times 330 minus L plus 10L equals 2400, and then solve. That's by substitution. If you were to solve it by the addition method, how would you do it there? Well, you need to get one of these variables to cancel out. So that means adding things together like 5 and -5, or 10 and -10. Personally, if I was doing this by the addition method, I'd multiply the top equation by -5 and get -5s minus 5l equals -1650. Add to 5s plus 10l equals 2400. 5l equals 750. So L equals, it'd be what, 150. And S turns out to be 180. And you get that by substitution. Substituting this back into, say, here. All right, so make sure you can do the addition method and the substitution method when it comes to time for the exam. But on any one particular problem, you're only going to be doing one. Figure out which one you find most convenient. Okay, let's try problem number 34. In fact, I think I'm going to want you to try problem number 34. Yeah. So, talking about movie tickets in a theater, and I've already given you some definitions here. G is the number of general admission tickets sold. S is the number of senior tickets sold. So there's 2 prices. General admission is $10. Seniors is $6 per ticket. For a particular show, there was 190 tickets sold at a net receipt of $1,740. Both of these numbers are going to help you come up with some equations. See if you can't figure out two equations and two unknowns to solve here. Trying to write down the two equations. You're going to use both of those numbers there. If you get the equations, you can actually spend time trying to solve it. Okay. So we need two equations. The first one that I'm going to write down is going to come from here. There's a total of 190 tickets sold. So the 190 represents the number of general admissions plus the number of senior tickets sold. So that's one equation. G plus S equals 190. The other equation comes from how much we earned in receipts. There was $1,740 in receipts. You get $10 for a general admission seat, $6 for a senior seat. So let's put those in as well. Our two equations look like this. G plus S is 190, and 10G plus 6S is 1740. Yay. And again, you can solve this any way you'd like. You can even graph it, although that'd probably be really, really tedious. If you do take the time to solve this, the general admission seats, 150, and the senior seats would then be 40. So that'd be the solution there. We're working on the setup here. Are we okay with the setup? Okay. Let's see, 2 here. We're going to next work with some distance equals rate times time problems. Distance equals rate times time. Okay, let's just kind of get familiar and comfortable with this stuff with an example or two first. Suppose you're going to drive up north to, say, Mackinac, and you look at Google Maps and it tells you it's about 280 miles up I-75 to Mackinac. So 280 miles, that's your distance. You want to spend 4 hours traveling. You want to say, you know what, I want to knock this out in 4 hours. What should your rate be? How fast should you be averaging? Well, 280 equals R times 4, or better yet, 4R. How would you solve? Divide by 4. 280 divided by 4 gives you 70. Which in Michigan would probably put you in the slow lane, but that's okay. 70. What units would go with that? Miles per hour. All right. I'm not sure if you saw it, but a year or two ago, there was a movie out called Martian. Anyone see that one? Yeah, it's pretty good. The interesting thing is that it took him 11 minutes to kind of phone home. It took 11 minutes for his signal to reach from Mars to Earth. And I was kind of curious about that. So let's do another distance equals rate times time problem here. This way. So the distance from where he was to Earth, don't know. But we do know a couple things. That it took 11 minutes for his voice to reach home. And that radio signals travel at 186,000 miles per second. Wow. That's pretty fast. So how far away from home was he? Well, good question. Let's turn the 11 minutes into units of seconds. So 11 minutes. There's 60 seconds in 1 minute. So notice what I'm doing. I'm multiplying effectively by 1. And the units that I want to cancel are in the denominator. So I end up with 660 seconds. Almost there. Distance equals rate times time. So distance equals rate times time, and that's going to be 186,000 times 660 seconds. So this actually be 186,000 miles per second times 660 seconds. Units of seconds is going to cancel itself out. And you get a very neighborly 122 million miles and change. That'd be an awkward conversation to hold. Because it takes 11 minutes for your signal to get there, and then another 11 minutes to get back. So can you imagine saying something and then waiting 22 minutes for an answer? That would be annoying. All right. I think I would start anticipating a few things. Now, these are just kind of some warm-up problems. We're going to do 2 problems out of the book here. But I just wanted to get you a little bit comfortable with distance equals rate times time. It's stuff that's actually out there. When we're working with these things, a lot of times it's helpful to summarize things in terms of a table. So, problem 42 is not an exception. We're going to be talking about a plane, flying into and flying with the jet stream. So I'm going to suggest a couple variables. We're going to let, let's do x is the rate of the plane in still air. And w is going to be the speed of the wind. So those are our 2 unknowns. We need to figure out both of these things, and I'll show you the problem in just a second. We're going to be looking at 2 different things, with the wind and against the wind. Distance, rate, and time. Our goal is to see if we can't fill in this chart. See if we can't fill that in. If we can, we'll have a good chance of being able to solve here. All right, so let's take a look at the actual problem then. Problem number 42. The jet stream is a strong wind current that flows across the United States. Flying with the jet stream, a plane flew 3,000 miles in 5 hours. Against the same wind, the trip took 6 hours. Find the speed of the plane in still air and the speed of the wind current. So let's take another good look at this. Flying with it, we flew 3,000 miles in 5 hours. Flying against it, we flew for 6 hours. How far did we fly when we were flying against it? Same distance. All right, so let's take a look at what we can fill in. Flying with it, 3,000 miles, 5 hours. Flying against it, 3,000 miles, 6 hours. There's still something I need to put in here for the rate. Now, the rate is really a combination of 2 things, right? It's a combination of your speed, speed of the plane, and the speed of the wind. So if I was going to write the rate down here when I'm traveling with the wind, what would it be? What should I use? Well, it's going to be x, the speed of the plane. If you're traveling with the wind, is the wind going to be helping you or fighting you? Helping you. So what should I do to account for the wind here? Plus W. The wind's helping you. How about here? Traveling against the wind. X minus W. Yay. This is going to give us our 2 equations because distance equals rate times time. So distance equals the rate times the time. Let me pause for a second. Make sure you're with me on all this. You okay with where I got this stuff? The 3,000 came from the problem. This came from the problem. What you have to understand is how the rate works. The rate is 2 things. It's your speed plus the wind or your speed minus the wind, depending if you're going with or against it. Okay. What equation does that represent then? It represents 3,000 equals, let me just change the order here, 5 times x plus w. What's the second equation? 3,000 equals 6 times x plus, or x minus w. That's a minus there, sorry. So those are your two equations. That's the tough part in these types of problems, is setting up those equations. I'm going to have you do problem number 44 in just a minute. So if there's something you're a little bit unsure of here, let's try and get this one done properly. Make sure you understand it before we move on to problem 44. As far as solving it is concerned, the inclination for a lot of people would be to distribute the 5, distribute the 6, and then solve. There's nothing wrong with that at all. Let me suggest here, though, that if I was solving 3,000 equals 5 times x plus w, personally what I would do, instead of distributing, I'd just divide both sides by 5. Because then I would get 600 equals x plus w. The 5's canceled out. I'd do the same thing here. I'd divide both sides by 6 in this equation. And this time I'd get 500 equals x minus w. So 3,000 equals 6 times x minus w. Divide everything by 6. And we end up with 500 equals x minus w. So this system of equations down here, these bottom two, are equivalent to solving this system of equations up here. This is just a little friendlier. You don't have to do it that way. 600 equals x plus w. 500 equals x minus w. If you divide both sides by 2, you get x equals 550 miles per hour. That's how fast the wind is blowing. Or excuse me, that's how fast the plane is traveling. If x is 550, can you see from that second equation what y would or what w would have to be? 50. So w is 50. So we got two solutions. You've got w is 50 and x is 550. If you substitute into here, so 600 equals 550 plus w, subtract 550 from both sides. Yeah, I can go into either one. If you put it in here, then when you subtract it, you get negative 50 equals negative w, and then you divide by negative 1 and just look at the same thing. Your turn for problem number 44. Very similar. See if you can't set it up. If you get it set up, then try and solve it. Okay. All right, I'm gonna walk around, try and help out. See if you can't set it up. I would suggest that you set up the same distance equals rate times time thing that we did with the last one. So width against distance, rate, and time. See if you can't set that up for this one. Downstream, you're traveling with it. So personally, I'm going to use two variables. I'm going to use S and C. Speed of the boat, speed of the current. Okay, so I'm going to use two variables here. I'm going to use S for the speed of the boat in still water and C for the speed of the boat or speed of the current. So let's see if we can't fill this stuff in. So you're either traveling with the current or against it. Distance equals rate times time. The distance both ways is what? 24 miles. Now, traveling with the current, it only takes 2 hours. Traveling against it, it takes 3 hours. The big question is, well, what should I put in for the rate? And I think I mentioned I was going to use variables S and C. So that's going to be the speed of the current. That's the speed of the boat in still water. Speed in still water. If you're traveling with the current, is the current going to be helping you or hindering you as you travel with the current? Helping you. So that's going to be S plus C. This will be S minus C. Might not be a bad idea to put these in parentheses. Distance equals rate times time. And that's going to give you your two equations. 24 equals S plus C times 2. 24 equals S plus C times 3. So 24 equals 2S plus 2C. 24 equals, oops, that should be a minus here, shouldn't it? Three S minus 3C. Just a little copying error. It's up to you how you want to solve it from here. Let me actually solve this one because it's a good example of something we didn't get to do in section 4.3 all that much, and that is work with something like this. If you did it this way, and you look at that going, I don't feel like doing this by substitution, you can do it by the addition method. The thing about using the addition method is that you need to have two variables that have the same coefficient and opposite signs. And what it boils down to is try and find the lowest common multiple for a pair of variables. What's the lowest common multiple for the numbers 2 and 3? 6. These are already opposite in sign, so here's what I'll do. I'll multiply the top equation by 3. Why am I multiplying the top one by 3? Well, because I want to get that lowest common, least common multiple. So that's going to be 72 equals 6S plus 6C. What should I multiply by on the bottom one? By 2. So that's going to give me 48 equals 6S minus 6C. So the important thing to see here is that in solving, sometimes you need to multiply both equations by a variable. And we did that here. Adding these together, I get 120 equals 12S. So what does S equal? 10. And that's going to be in units of miles per hour. Now S is 10, that's part of our solution, but we're not done yet. We need to figure out the rest of it. Okay, so let's look at the rest of it. Plug in an S equal 10 up here. 24 equals 10 plus C times 2. You can distribute the 2, or I think I'm going to choose just to divide it out by 2. I'll get 12 equals 10 plus C, and then subtract 10. How fast was the current? Good. 2 miles per hour for the speed of the current. So kind of a loaded example here in terms of, things that you can pick up out of this one. The most important thing is the setup for this distance equals rate times time stuff. Speed of something in still water, still air, going with it, so you're adding the current, going against it, you're subtracting the current, etc. They gave you 2 equations and 2 unknowns. The other thing that you can pick up on this is that when you're solving 2 equations and 2 unknowns, these 2, the one in the green bracket, the one in the pink bracket, you can multiply both equations in order to finish solving here. So I multiplied by 3 in the top and 2 in the bottom. That gave me a 6C here and a minus 6C. That's what I wanted. I needed to engineer these things to have the same coefficient but opposite sign. Whew. All right. Anything else on problem number 44 here before we move on to mixture problems? I think I warned you at the start of class that this would be the longest section. The next section is going to be friendlier. It's going to be mostly review. But this one, yeah, a little bit of a pain. Yeah, some polite agreement with that. Okay, so let's work on mixture problems. Okay. Mixture problems are going to be things like you've got one blend of gasoline, you're adding a different grade of gasoline to come up with some hybrid mixture. Or you've got a certain strength of solution that you're using in a photo lab. You're adding a different strength, you're getting a different concentration. How do you come up with these hybrid concentrations, etc.? Okay, well, I think we'll start with problem. Let's see which one do we want. 48. There we go. So the pharmacist has a mouthwash solution that is 6% ethanol alcohol and another is 18% ethanol. How many milliliters of each must be mixed to make 750 milliliters of a mouthwash that is 10% ethyl alcohol? All right. I like to approach these things with pictures. I like to kind of depict what's happening with a set of diagrams with some circles. You're going to start by adding 2 solutions together. There's a 6% solution, and you're going to add an 18% solution. When you combine these, you're going to get a new solution. What can you tell me about that new solution? It's going to have 10% alcohol. So what I'm doing is I'm trying to graphically represent these problems. Now you're going to end up needing 2 variables to solve these kinds of things. In the first half of this, and I've put these little half moon kind of shapes here, or crescent moons, in each of these circles, you're going to write the percentage. Or later on, we're going to write the price. So this is a 6% solution. This is an 18% solution. That's a 10% solution. In the second part of this circle, you're going to write how many milliliters of solution. And we're going to do that for all these. How many ml of solution? Do we know how much 6% solution that we're using? No. So I'm going to put an X here. Do I know how much 18% solution am I using? No. But they tell us that we're going to end up with 750 milliliters of solution. That's how much we're going to end up with. That comes from the book. There's two unknowns. How many milliliters of this? How many milliliters of this? So if there's two unknowns, how many equations do I need? 2. Now the first one kind of reads itself off. If you have X milliliters of solution here, and you add, oops, I put an X here. This should have been a Y. That's really bad. I might have even said Y, I'm not sure. X plus Y. What does X plus Y have to equal? Good, 750 milliliters. So that's our first equation. So X plus Y equals 750. The next equation you get if you actually took the time to calculate how much alcohol is in this. The alcohol here comes from the alcohol here plus the alcohol here. Well, how much alcohol is in here? 6% of this. So it's 6% of X plus 18% of Y equals 10% of 750. So there's your two equations right here. Now you can solve those any way you'd like. It's up to you. But there's your two equations. The first one just comes from adding them up. This plus this equals this. The second one you get from this times this plus this times this equals this times this. And it works out pretty nice. The solutions in this case would be X is 500 milliliters and Y is 250 milliliters. Now that solution I'm not showing how we arrive at it. You can use addition, substitution, graphing, a lot of choices there. There is one thing I want to discuss about this a little bit more, and I'll do that in a second. But let me give you a chance to ask anything that you'd like clarified a little bit more. Autumn?
So are we just trying to get the equations down?
On the exam, you're going to have to solve them. But in class right now, I'm only spending time practicing the setup. Because I know that's going to be the hardest part for you, is setting it up. I'm hoping that once you get it home, I mean here, I'd probably use, substitution or addition to solve. I mean, it's not too bad if you multiply this by -6, this whole equation, add it to this one, you get the 6's cancel out, you solve right away. Right. The equations themselves won't be that hard to solve. One question that I got in my morning class was, well, wait a minute, what happened to the percentages? Isn't 6% 0.06, right? How come I didn't use that? How come I didn't use 0.18 here or 0.10 here? And the answer is you can. So here it is. Here it is with all those extra things in here. If I do 0.06x plus 0.18y equals 0.10 times 75, then instead of this equation, I get this one. But if I was stuck with this equation, I'd probably multiply it by 100, right? And guess what? I'd be back over to where we were. So rather than put in the decimal and then take it out, I just leave it out. So if you're a little bit bothered by the fact that, gee, we didn't use the decimal, we didn't use percentage, technically we did. Or you could think that we did. By putting it in and then multiplying by 100, really brings us to where we are here. So I think it's just more convenient not to put it in at all. All right, we're going to do a similar one to that. And this is going to be the last one for this section. So your chance to try and work on some of these things. This is going to be another mixture problem. We're going to mix peanuts and cashews this time and get some kind of a mix. It's going to be problem number 50. Let me draw this here for you. Give you a chance to copy it down before I put up the problem. What I want you to do is try and fill in these and come up with the two equations. It's going to be similar, but it's still going to be a little bit different as well. You might have to do a little bit of thinking. All right, so problem number 50. This is a merchant wants to mix peanuts with cashews. Shown in the illustration, to get 48 pounds of mixed nuts that will be sold at $6 per pound, how many pounds of each should the merchant use? All right, well, instead of having percentages, like a percentage of alcohol, we have the cost. Cost is $3 a pound here. $6 a pound for cashews, which of course are delicious. And then we're going to end up with a mixture that's going to be sold at $6 per pound. So that's kind of your final thing there. See if you can't put these all together and figure out your system of equations. Fill in those circles, those half circles. I'll walk around and help out. Okay, so we're going to end up with 48 pounds. So let's keep track of that information. Oops. Zoom out. So peanuts cost $3 a pound. Cashews cost $12 a pound. The mix is going to sell for $6 a pound. So fill in part of it. The other part. Do we know how many pounds of peanuts we're going to use? No. And I liked what a few of you did. A few of you said, all right, I'm going to use a variable that reflects the problem. So here, instead of using an X and a Y, used a P and a C. We do know how much we're going to end up with, though, right? We're going to end up with 48 pounds of mixture. So that 48 pounds comes from adding the number of pounds of peanuts we have, plus the number of pounds of cashews, equals the number of pounds in our mix. So P plus C equals 48. Now if you use X plus Y as 48, same thing, that's fine. The next thing is to figure out how much this is all going to cost or sell for. So it's going to be 3 times P plus 12 times C equals $6 times 48, 288. So P plus C equals 48, and 3P plus 12C equals 288. And there's your system of equations. If you actually worked it out, you end up with P equals 32 pounds and C equals 16 pounds. Okay. For homework, in section 4.4, try problems 3 through 9, 17 through 27, 31 and 33. So you've got a couple distance equals rate times time problems. Those are 41 and 43, and a couple mixture problems. Don't skip those, 45 through 51. Good luck.